each component functions in a glycol dehydration unit. Now let's look at glycol conditioning and how glycol losses can be reduced. This is the third section of a three-section module on glycol dehydration unit operation. In this section, we'll examine the importance of glycol conditioning, operational procedures, and potential problem areas within the system. Various temperature and pressure conditions affect how efficiently the glycol dehydration unit can operate. First, let's look at operating temperatures in the contactor, reboiler, and still overhead. Then we'll look at operating pressures. In the contactor, the temperatures of the inlet gas and the glycol affect the amount of water removal from the saturated gas. Now, if you recall, at constant pressure, natural gas can hold more water as the temperature of the gas increases. And what does that mean? Well, it means if we keep the inlet gas temperature low, the unit will have less water to remove from the gas. Now, you also want to keep that lean glycol temperature down to a minimum when entering the contactor, but still 10 to 15 degrees Fahrenheit higher than the inlet gas. Why? Well, for several reasons. 1. Warm glycol absorbs water more easily than hot glycol. Secondly, we're trying to keep the temperature of the gas cool, so the incoming gas has less water in it. And thirdly, this helps to prevent hydrocarbon condensation. Now, the reboiler temperature is important because it controls the concentration of water in lean glycol. At constant pressure, higher reboiler temperatures result in greater glycol purity. The temperature range for TEG should be set at 380 degrees to 400 degrees Fahrenheit. Why? Because we want the range higher than the temperature where water boils, 212 degrees Fahrenheit, so that the water can be removed quickly, but lower than the temperature where glycol degradation begins, 404 degrees Fahrenheit. Remember what the still column does. It removes water from rich glycol, and it recaptures glycol trying to leave with water vapor. The temperature range we want to set for the still overhead temperature is between where water boils and where glycol boils. It's easy, because water boils at 212 degrees Fahrenheit and triethylene glycol boils at 546 degrees Fahrenheit. The recommended range for the still overhead temperature is 212 degrees to 215 degrees Fahrenheit at sea level. Low still overhead temperature can cause reboiler overload and excessive fuel consumption. High still overhead temperature can cause glycol loss due to vaporization. Now let's look at operating pressures in the contactor, regenerator, filters, and GCG separator. If you operate the contactor below the proper design pressure, you will have problems. First, at constant temperature, water content of inlet gas increases as pressure decreases, causing the unit to work harder to dry the gas. Secondly, at constant gas rates, the gas velocity through the contactor increases as the pressure is decreased, causing carryover problems. Regenerator pressure will build up if there's a plugging or flooding problem in the still packing. An increase in regenerator pressure prevents some water from boiling out of the glycol, requiring higher temperatures in the reboiler. This wastes fuel gas and can lead to glycol degradation. As far as your filter goes, a pressure drop of 3 to 6 psig is normal as glycol flows through the elements. The pressure differential increases as the elements become plugged. Replace the filter elements when this differential increases to 15 to 20 psig. Operating pressure in the gas condensate glycol separator is 50 to 85 psig. Back pressure is maintained by a pressure-controlled regulator. Okay, now that you understand the various temperature and pressure interrelationships, you should be able to prevent costly operating problems such as high glycol losses, foaming, and corrosion. To really operate efficiently, you've got to minimize your glycol losses. Losses occur due to vaporization, entrainment, and mechanical leaks. Typical conditions which affect glycol losses include carryover with outlet gas leaving the contactor, leaks at the pump and pipe fittings, high still overhead temperature, the contactor column operating at excessive gas rates, foaming, and rapid changes in the gas rate. But how do you know if you're operating efficiently or not? Well, you take glycol samples in the field, have a laboratory test them, interpret the results, then you make the necessary adjustments to reach maximum drying efficiency. Now you can find out a lot by analyzing the glycol. Now it can tell you glycol weight percentage, water content, hydrocarbon content, salt content, solids content, pH of the glycol, iron content, and foaming tendencies. Let's look at a lab analysis from a typical glycol dehydration unit and see how efficiently we're operating. The glycol weight percentage refers to the amount of glycol in the glycol solution, also known as glycol purity. Lean glycol should contain about 98.5 to 99.9% glycol. Rich glycol content varies from about 93 to 96% glycol. Well, looks like our rich glycol sample is in the acceptable range, but the lean glycol is outside the acceptable range. This means there may need to be some adjustments made. Water content refers to the amount of water in the glycol solution. Low water content in lean glycol is vital to good dehydration. The water content in lean glycol should not exceed 1.5%. If the water content exceeds 1.5%, then the reboiler temperature is too low and/or a heater is not working properly. The water content in rich glycol should not be more than 5 or 6%. Let's take a look at our sample. The water content for the rich glycol is acceptable. However, the lean glycol water content is too high. Again, this means that some adjustments may need to be made. Water content spread refers to the difference in water content between lean and rich glycol. A spread which is too narrow, 0.5 to 2%, usually means the glycol circulation rate is too high. The rate should be lowered to save energy, minimize glycol losses, and improve dehydration. A spread over 4 to 6% is too wide, and usually means the glycol circulation rate is too low and should be increased. The water content spread between our samples, approximately 3%, falls in the acceptable range. A good guideline for circulation rate is, for every pound of water to be removed, use 3 gallons of glycol. Hydrocarbon content refers to the amount of oil, paraffin, or condensate in the glycol. Keep it below 0.1%. Otherwise, problems such as foaming, plugging, or fouling will cause glycol loss and poor dehydration of the gas. The hydrocarbon content in our samples is below the range. Hydrocarbons get into the glycol in 2 ways. By condensing in the contactor when the glycol is colder than the incoming gas, and by carryover of hydrocarbon contaminants from the inlet separator or gas stream if the unit has no separator. Salt content refers to the amount of salt or chloride in the glycol. It should be kept below 0.01% by weight, or 100 parts per million. Problems occur when the salt content reaches almost 0.1% by weight, or 1,000 parts per million. These problems include a buildup of salt on the reboiler fire tube, resulting in decreased heat transfer efficiency, corrosion, which will eventually decay the fire tube, and hot spots on the fire tube, resulting in thermal decomposition of glycol and holes in the fire tube. Although the salt content of our samples is a little high, it is still in an acceptable range. Salt usually travels in the gas stream in a fine mist. Now, if the gas stream contains excessive salt, a coalescing or filter-type separator can be used to remove salt from the gas upstream of the dehydration unit. Solids content refers to the amount of suspended solids in the glycol. Suspended solids should be kept below 0.01% by weight using filtration. High solids content in glycol cause the following problems: increased pump wear from abrasion, accelerated corrosion and erosion, increased fouling of the fire tube, increased glycol loss due to foaming, and increased plugging problems. The solids content of our sample seems to be in the acceptable range. pH refers to the corrosiveness of glycol. pH is a term used to express acidity or alkalinity. It is based on a 0 to 14 scale. 0 to 6.9 is acidic, 7 is neutral, and 7.1 to 14 is alkaline. A pH of about 7.3 is considered a safe operating level. As glycol pH decreases, the equipment corrosion rate increases rapidly, and troublesome corrosive compounds result. Raising the pH above 8 to 8.5 is not desirable because a more alkaline glycol solution tends to foam and emulsify easily. In our sample, the pH of the lean glycol is acceptable at 7.4, but the pH of the rich glycol is too acidic. Check the pH of the glycol periodically and keep it on the alkaline side by neutralizing the acid compounds with alkaline chemicals. Iron content refers to the amount of corrosion products in the system. Rust is the most common. Corrosion products either come in with the incoming gas or they are the result of a corroding glycol system. If the iron content exceeds 10 to 15 parts per million, then corrosion prevention methods should be considered. The iron content of the rich glycol at 5 parts per million and lean glycol at 4 parts per million is acceptable. Foaming refers to the foaming tendency of glycol caused by contaminants. These contaminants in the glycol enter the system as gas entrainment. Water and glycol alone will not cause significant foaming. However, the combination of water, glycol, and oil does create excessive foaming. The main problems associated with foaming are improper gas dehydration, excessive glycol losses when the glycol foams out of the contactor, and additional equipment problems downstream of the contactor from glycol carryover. Foaming problems can temporarily be corrected by anti-foam additives, which cause the foam to break. The cause of the problem should then be identified and corrected. Improper use of anti-foam additives can increase foaming problems. The best preventative measure against foaming is the installation of a properly designed inlet gas separator and glycol filtration system. Good glycol filter maintenance and pH control are also very important. Well, that concludes the third section. In this final section, you saw how important temperature and pressure conditions can be, how to reduce glycol losses, and how glycol tests can pinpoint problem areas. Now read over the last section in your student manual. Review this videotape if needed. Then when you're ready, answer the questions at the end of the section. During this program on glycol dehydration unit operation, you've had the opportunity to review principles of glycol dehydration, to examine the system components, and to see how to properly operate a unit. Now, if you require additional information, there is an appendix at the end of the third section in your student manual, which includes a troubleshooting guide, a safe lighting procedure for a gas-fired glycol dehydration unit, recommended startup and shutdown procedures, and a chart showing water vapor content of saturated natural gas. A glycol dehydration unit uses several processes to separate water, hydrocarbons, and other impurities from natural gas. By properly maintaining your equipment and knowing what problems to look for, you can make the difference in successful natural gas processing. By understanding the various components in your glycol dehydration unit, and by knowing how to make the necessary adjustments, you can dry natural gas to the desired level and reduce your glycol losses while operating efficiently, cost-effectively, and most of all, safely.